So we are in the middle of constructing the molecular orbital diagram of beryllium hydride. And we said in the last video that because we have three different atoms here, we have to come up with what are called symmetry adapted linear combinations of the terminal atoms, orbitals that are going to be involved in bonding. In this case, for hydrogen, we only have 1s orbitals. Hydrogen only has one electron, valence electrons are only in 1s. And the next available orbitals, the 2s, that's going to be too high in energy. You've gone from n equals 1, going back to your quantum numbers, right, to n equals 2. So those are too different in energy. So we just have to care about the 1s. We did some work here to figure out the symmetry of our two salts, which are going to be sigma G plus and sigma U plus. One thing I wanted to mention is that we had two 1s orbitals that we're trying to combine, right? One from each hydrogen, and we ended up with two salts. So it's kind of the conservation of, whatever number you start with, you have to end up with that same number. Think about when you take two atomic orbitals, you make one anti-bonding and another bonding orbital, right? So if you started with two atomic orbitals, you ended up with two molecular orbitals. Similar thing here. And here's what they look like. Here's the sigma G plus, and here's the sigma U plus. Okay, so now we are ready to begin constructing our diagram. And so for our MO diagram, we now have kind of two asymmetric things, right? It's not like before where we had two oxygen atoms or something like that. Now we have beryllium and we have hydrogen. Now the beryllium atom is going to have 2s and 2p's. Those are valence electrons are in the n equals 2, so we have to look at the 2s and the 2p's. How did we get these symmetries? Sigma G plus for 2s and pi u and sigma u plus for the 2p's. Well, that comes from the character table, right? Remember that s orbitals always are spheres, so they transform totally symmetrically. So that's going to be sigma G plus. That's why we have sigma G plus here. And then the px, py, pz orbitals are going to transform as the x, y, z vectors. So you can see here in this point group that x and y, px and py are going to transform together as pi u, and the pz is going to transform as sigma u plus. So that's why we have pi u plus sigma u plus there. Now we have our hydrogen salt symmetry, sigma G plus sigma U plus. Again, that came from all the work we did down here. The last thing is, how do you organize the energies? Well, we can look up the energies. And where does this come from? This comes from ionization energy. I mean, there's lots of ionization energy data out there in the literature. And so, if you think about what is the energy of an atomic orbital, all that is the energy it takes to eject an electron out of that. So that's the ionization energy. So you can just use ionization energy. We see that, right, you have more stabilized values as you get to higher atomic numbers. We talked about that before. Really what we're interested in here is the values for hydrogen, right? So for hydrogen, it's 13.6. This is in electron volts. This table is in electron volts. And that's for the 1s. For beryllium, it's going to be 9.3. Now notice there's no value given for the 2p orbital of beryllium. Why is that? That's because beryllium doesn't have any electrons in its 2p. Okay, there's only 4 electrons in beryllium, and so you have to get to 5 electrons to carbon to get an electron in boron, sorry, to get into electron into the 2p. So experimentally, in terms of if you're just using ionization energies, there's no 2p value. But we know that the 2p is always higher than the 2s, and so it's going to be some value above 9.3. All right, so what we can do is we can write negative 9.3 EV for 2s. We got that from the table. 2p, we don't know exactly where it is, but we know it's going to be higher than 2s. So this is the next thing, is to arrange the atomic orbitals and the salts in order of their relative energy. For the hydrogen salts, this table was for a lone hydrogen atom. And so you might be wondering, well, now I have a sulk. Is it actually going to be negative 13.6? And I'm using negatives here because, again, a higher number means more stabilized. Yes, it is going to be very close to negative 13.6. And the reason is because these hydrogen lobes that we're drawing here of electron density are very far apart. Remember, there's a beryllium atom that's going to be in the middle there, central atom. And so these lobes aren't interacting with one another. It doesn't matter if this is the sigma U plus sulk, which looks like it's setting up an anti-bonding interaction maybe. And this is the kind of, the more symmetric one, the sigma G plus. It doesn't matter. They're all going to be the same. They're degenerate 13.6 because those lobes are far apart, right? They're not interacting with one another. So that's what this says. Since H to H distance is very long, energy of sulks is about equal to that of constituent AOs. So you can use just the ionization energies from that table I showed you. All right, so now the next thing is to mix orbitals and determine their symmetries. And so how do you mix orbitals? You mix orbitals that have similar energies and same symmetries. So here we have a 2s orbital with sigma G plus, and we have one of these sulks, the top one, that has sigma G plus symmetry. That tells us, since the symmetry, they're both sigma G plus, we can go ahead and mix these. And we're gonna make a bonding interaction. So we're gonna add them, constructive interference, and we're gonna make an anti-bonding interaction, just like any other atomic orbitals. So sulks, fundamentally, they're still atomic orbitals. They're just different combinations of atomic orbitals. All right, so now we have to give these labels. And how do we figure out that these are sigma G pluses? It's not just because this came from a sigma G plus. Remember, we use lowercase sigma here, a capital sigma for the atomic orbitals, lowercase sigma, lowercase letters, sigma in this case, lowercase letters for the molecular orbitals. How do we figure that out? Again, this one I think you can kind of see. It's basically a big sphere. Well, it's a linear kind of spheroid thing. But that's going to have the same symmetry as a regular sphere. For this case, right, you have to go through and you have to do the symmetry operations. And so I'm just going to remember what that molecular orbital looks like. I'm going to go back to the D infinity H character table here. And so let's actually work through this, right? So we have something that looks like this. So our molecular orbital, right? And so rigorously what you'll have to do is you'll have to apply all the symmetry operations to this molecular orbital and see how it transforms. Now, I'm doing this slowly for the sake of lecture, but you can do it pretty quickly in your head. But when you write it all out, like I'm going to be writing it just to demonstrate to you, it takes some time, right? So obviously, if we do identity on this, we're going to get a 1. So that's there. Let's do a C infinity. Right? If we do a C infinity on it, well, the C infinity runs through here. It's a rotation. If we rotate that way, nothing's going to happen. These are spheres, right? So we're going to get back the same thing. That gives a 1. What about a sigma V? Sigma V is a mirror plane through here, right? So again, that's going to get back the same thing. That's why you have a 1. Now, what about inversion? Okay, inversion, well, you're going to put left to right and right to left. Well, that was light shaded to light shaded and light shaded to light shaded. And then middle to middle, that's dark to dark. So inversion doesn't do anything. So that's why we have a 1. And then we have here S, the improper rotation. Well, remember that an S improper rotation is a C infinity. This is going to be a C infinity. C infinity we showed did nothing. And then we're going to do a mirror plane, sigma H. So that's going to go through here. That's going to take that light to that light and, not do much to this center lobe. So that also is going to give you back the same thing. So you get a 1. And then lastly, I'll do it up here. You're going to have your C2. Your C2 is perpendicular there. It's a 180-degree rotation. And so that's going to take light to light and light to light, and the dark is just going to spin around. So again, you're going to get back the same picture. So that means you have a 1. So that shows us that this molecular orbital has the symmetry sigma G plus. But you have to do this. You have to go through and think about how it transforms. You can't just say, hey, this is a sigma G plus here, this is sigma G plus here, so I'm going to get sigma G plus there. Sometimes the symmetry would change. And indeed, it did change if you remember going back to the diatomic examples. And there'll be many other examples where it does change. All right, what's next? Next, we have a pi u here, okay? And we also have a sigma u plus here. What can bond? Same symmetries. Sigma u plus, similar energies, okay? And so we're gonna make bonding and anti-bonding versions here. So this would set up a bonding interaction, right? Where we have light overlapping with light and dark overlapping with dark. And this we have, anti-bonding interactions where we have light with dark and dark with light. What is the symmetry of those? Again, if you transform these, it's going to be sigma u plus. And the only way to show that for sure is to do the same logic that we just did, going through how it transforms, okay? So that's fine, and now we are left with these pi u's, and we didn't use these pi u's. There's nothing left to bond with. We don't have any salts. And so those just kind of slide over. They don't change in energy, and those are non-bonding orbitals, okay? And again, I'll use a lowercase pi there. I put a little n to signify non-bonding. Sometimes you'll see n or nb. These are anti-bonding, so I put stars, right? Last thing to do is number the MOs. So this is our first sigma G plus in the diagram, so give it a 1. This is our second sigma G plus in the diagram, give it a 2. First sigma U plus in the diagram, give it a 1. Second sigma U plus in the diagram, we're just counting the number of orbitals with the same symmetry and ordering them numerically with increasing energy. This is going to be the 2 sigma U plus. And there's only 1 pi U orbital with that symmetry, so we'll call it the 1 pi U. Now you got to populate with electrons. How many electrons do you have? You have 1 for each hydrogen. Well, you got 2 hydrogens, so you got 2 total in salts. And in the 2s orbital for beryllium, you've got 2 electrons. Now you have 4 electrons total in beryllium, right? It's element number 4, and so that's a 1s down here. But that's a non-bonding one, right? And so we don't really care about this because those are core electrons. Okay, so you don't, we won't really be focusing on the core electrons, what's happening there. And you're not going to be bond, even though it has the same symmetry. This s orbital, right? All s orbitals have sigma G plus. It's not going to bond with this sigma G plus salt because it's too different in energy. They'd much rather bond with the 2s because it's pretty similar in energy. That amount of about 4 EVs, that's similar enough to have constructive overlap. Anyway, so you have 2 valence electrons in beryllium, 2 valence electrons for the 2 hydrogens. That means you have a total of 4 valence electrons. We could write out the electron configuration for this molecule just like you would for an atom. But now instead of saying 1s2, 2s2, 2p6 and all that, now we're saying 1 sigma G plus 2, 1 sigma U plus 2. Okay, that's the electron configuration. And we could do the 1.5 times the number of bonding electrons minus the number of non-bonding electrons. And you'd get, there's 4 bonding electrons. There's no anti-bonding or non-bonding electrons. So that gives you 2 bonds. That corresponds to, your classical Lewis structure of beryllium hydride, which looks like this, right? And you may remember from VSEPR, our Lewis structure rules, beryllium is an electron deficient atom, and it's a lot of times it doesn't have an octet. It only has 4 electrons. So with that, we were able to, for the first time, use salts and come up with this MO diagram for beryllium hydride. In the next video, we're going to go to a more complicated example where we'll do methane, but same fundamental principles will apply.